And the next talk is going to be by Adisa Bulatek.
All right, hello. Okay, can you see me and hear me and see my slides?
Yes, everything is
Great.
good.
Awesome. Thank you so much. Okay. So, hello, everybody. First of all, I'd like to thank the organizers for organizing such a wonderful and informative conference and for allowing me to contribute. My name is Alyssa Bulatek, and I just finished my first year of graduate school at the University of Florida, working with Dr. Adam Ginsberg. And I'd like to take the next 8 or so minutes to tell you about a project that I worked on for about the past year, which aims to answer the question, which spectral lines trace what physical processes in the Galactic Center? Building a toolkit brick by brick is the subtitle of my talk. So as we've heard in several talks so far today, astronomers use several molecules as heuristic tracers for different processes in the ISM. I've listed some examples here, but I won't go into great detail on them since a lot of these molecules have been discussed already. But we can trace processes like outflows, hot pre and protostellar cores, shocks, or dense gas with some of these different molecules. But a problem arises when we try to use these tracers to find these processes in the Milky Way's central molecular zone. And that happens because these molecules tend to be pretty widespread in the CMZ. As we can see in the circular figure at right, the structure of these molecules is really complicated. And it's kind of a unique environment where the emission from these molecules can be found far from the processes that they typically trace. So how do we trace outflows, cores, shocks, and diffuse gas in the CMZ if we can't use these traditional tracers? We need unique alternative tracers to be able to do this for this environment. One could do this by looking at a molecular cloud like the brick in the CMZ, which happens to contain examples of the 4 ISM processes we're interested in. Some examples of those processes are shown in the panels at right. And to do this, we wrote an ALMA proposal to conduct a wideband spectral line survey of a pointing in the brick. The goal of that survey is to build a toolkit of different tracers that can uniquely identify these processes. And we would ideally be able to apply that toolkit both in the CMZ and in intensely star-forming galaxies, which have environments similar to the CMZ. So I'd like to quickly mention Maya Petkova's recent paper on the brick, which demonstrates that the brick is of broad interest to the ISM community. Her work compared real ALMA observations to simulated ALMA observations of some common molecules in the brick. And they were able to differentiate between tracers of compact structures and more diffuse structures. That was one of their takeaways. And I think it would be cool to be able to compare these simulated images and moment maps of these molecules to the results that we get from our spectral line survey once we're done processing those data. So onto the survey, without further ado. Here is a coarse summary spectrum that I created of all the data that we have delivered so far. This was made by taking the max or maximum spectrum of all of our cubes. So essentially paring down the spatial axis to the maximum point at each frequency, turning that into a spectrum, and then binning the spectrum in 1 gigahertz bins to sort of get a coarse idea of what we're looking at. So what I plotted here is for each 1 gigahertz bin, the fractional bandwidth of that bin that's above the 7 sigma level, which we're using as sort of a proxy or indicator for like the spectral line richness at that frequency. And as we can see, we have pretty rich data. We have lots of spectral lines all across bands 3 and 4 and about half of band 6. And we've asked to fill in band 5, what we're missing in band 6, and also expand to band 7 at higher frequencies. The target resolution for the survey is 1 arcsecond, which is easily achievable across most of our bandwidth. And the sensitivity that we're going for is 0.25 Kelvin in 1 kilometer per second channels. And we've actually been able to use this sort of summary plot to validate the spectral setup of the ACES ALMA large program, which is a band 3 survey of the entire CMZ. Okay, so sort of the first step in zooming in on that coarse spectrum is to look at the individual max spectra for each spectral window that we have. And so we've done this for a few max spectra. We've looked at them closely. And in general, we see a lot of small molecules that you might typically see in a cloud like this. And we also see their isotope logs. So things like HCN, HNC, and NH2D, for example. We also see a couple more complicated molecules that I haven't shown here in these particular cutouts of the spectrum. We also see some masers, which is interesting. But in general, in what we've looked at so far, we haven't found anything too unusual, but we've really barely scratched the surface of what lines are in these data. We've also barely scratched the surface of what science we can do, which is really exciting. So one way we can start to differentiate the regions that trace these 4 different processes that I outlined earlier is to measure the temperature in this region of the brick. And one way to measure temperature is by using a temperature sensitive molecule like methanol or methylacetylene or methylcyanide. And we happen to have 7 methylcyanide ladders in our delivered data so far. And here I've created a rotational diagram using part of one of the ladders. And I'll note this is a preliminary fit. It looks a lot like that undergraduate lab report plot without error bars from the talk earlier, but we managed to fit a temperature that's kind of close to Dan Walker's recent result for the same pointing in the brick. So ideally, if we repeat this for other methylcyanide ladders and repeat this for each pixel in our cube, we can make a temperature map of the cube, which can then allow us to get measurements of the column density and the volume density across our pointing. So much, awesome, thank you. Much of this project is still probably wrapped up in the future work category. So in addition to making temperature maps, one immediate next step is to make moment maps of some molecules. We have some preliminary ones in the gray circular figures on the left of the figures here. We can start to make some basic differentiations between different morphologies for different molecules. So maybe some of the molecules look, I don't know if you can see my mouse, but maybe they look more diffuse versus they trace more compact structures. We might even be able to see, like preliminarily, we might be able to say we can see cores for some molecules. And also a next step would be to compare our data with the simulation data from Maya's recent paper to see if we can match structures for the same molecules. And finally, addressing the actual goal of the project, which is to determine which structures are associated with known locations of cores, outflows, shocks, and regions of diffuse gas, and to try to see which unique tracers we see in each of those locations. So thank you so much for listening and for having me here, and I'm happy to take any questions here or Slack or email. Thanks.
Thank you very much for the very exciting talk. Please, if anyone has any questions, raise your hand. Yes, Arcana?
Yeah, very quick question. So very nice talk, Aliza. So did you have the continuum, dust continuum maps also for brick, and were you able to resolve this brick with your sub-arcsecond or 1 arcsecond resolution from ALMA observations?
I believe we do have dust continuum maps from Adam. My advisor would be able to answer this better than I would, but yeah, I know we have dust continuum maps for this region. I don't know how recent they are, or what the resolution of those is, but
okay. Thanks.
Thank you.
Okay, if there aren't any more questions, let's move on then.